Hello everyone, and welcome back to the channel. Today, we are diving into one of the most ambitious transportation projects ever built in the desert. This is the Haramain High-Speed Railway in Saudi Arabia. But this is not just a train line, it is a 280-mile corridor, cut straight through one of the harshest environments on Earth, connecting two of the most sacred cities in the Islamic world. Before we continue, make sure to follow the channel, because here we break down the world's most incredible construction projects step by step, from empty land to completed megastructures. Now, let's begin. At first, there was only sand. Endless dunes, scorching heat, rocky plateaus, and open deserts stretching between Mecca and Madinah, with Jeddah and the King Abdullah Economic City positioned along the route. No tracks, no stations, no power lines, just raw terrain baking under temperatures that could exceed 122 degrees Fahrenheit. The mission was staggering. Build a railway capable of carrying trains at more than 186 miles per hour, smooth enough for comfort, strong enough for decades of use, and resilient enough to survive the sandstorms, flash floods, and extreme thermal expansion. For millions of Muslims traveling for Hajj and Umrah, this was not just infrastructure. It was meant to transform a journey that once took hours by car or bus into a fast, safe, climate-controlled passage across the kingdom. Before a single rail could be laid, engineers had to understand the desert itself. Survey teams moved across the planned corridor with GPS equipment, drones, and geological drilling rigs, mapping soil composition, rock hardness, dune movement patterns, and underground water tables. This was critical because Saudi desert terrain is far from uniform. Some sections sit on solid rock, others on shifting sand that can migrate meters per year if left unmanaged.
This soil sample shows why some areas need deep reinforcement.
Engineers needed to know exactly where the ground could support a stable trackbed and where it would require deep reinforcement. Climate data was just as important as soil data. Teams studied wind patterns, sandstorm frequency, seasonal flooding in low-lying wadis, and the punishing daily temperature swings that cause steel and concrete to expand and contract. Every decision, from route alignment to material selection, had to account for a desert that does not forgive shortcuts. This phase was quiet, with no cranes or concrete yet, but it was the foundation of everything that followed. Without a precise understanding of the land, the fastest railway in the Middle East could never have been built safely above it. With the ground understood, the real transformation began. Heavy excavators, grading machines, compactors, and convoys of dump trucks rolled into the desert. The empty corridor turned into a moving construction front stretching across hundreds of miles. The first task was taming the dunes. In many sections, loose sand had to be stripped away entirely and replaced with engineered fill. The fill was compacted in layers to create a stable foundation. This foundation was strong enough to carry high-speed trains without shifting or settling unevenly over time. But removing sand was only half the battle. The desert does not stay still. Wind constantly reshapes dunes, and left unprotected, drifting sand could bury tracks within days. Engineers designed long stretches of sand mitigation barriers, fences, and graded embankments.
These barriers redirect wind to keep sand off the tracks.
These were angled to redirect wind flow away from the railbed. In the most exposed zones, the route was elevated on embankments. This kept blowing sand from accumulating directly on the tracks. It was a constant, almost invisible battle between engineering and the desert wind. Water posed an unexpected danger in a place known for drought. Sudden desert storms can trigger flash floods through low-lying wadis. Wadis are channels that are dry for years and then fill violently within minutes. Crews built culverts, drainage channels, and elevated viaducts at every crossing. These allowed floodwater to pass safely beneath the line instead of overwhelming it. Dozens of bridges and viaducts were constructed along the corridor. Some stretched for miles, lifting the railway above terrain too unstable or flood-prone. This was necessary for a standard ground-level track bed. Once the foundation work was underway, track laying began in earnest. Specialized rail-laying trains moved slab by slab across the desert. They placed ballastless track systems designed for high-speed stability and minimal maintenance.
Ballastless tracks like these ensure stability at high speeds.
Concrete sleepers were set with millimeter-level precision. Even small misalignments become dangerous at speeds above 180 miles per hour. Steel rails were welded into continuous lengths to eliminate joints that cause vibration and wear. Rails were anchored to withstand thermal expansion and temperatures swinging dramatically. Temperatures ranged between scorching daytime heat and cooler desert nights. Overhead, electrification masts rose in long rows. They eventually carried the catenary wires that would power the trains. Signal cable trenches were dug alongside the corridor. Fiber optic lines were buried to support communication and control systems. Mile after mile, the desert that once held nothing began to take shape. A modern railway emerged, a thin ribbon of engineered stability. It cut through one of the most unforgiving landscapes on the planet. While the corridor pushed across the desert, an entirely different kind of construction was rising at its key points, the stations. 5 major stations were planned along the route: in Mecca, Madinah, Jeddah, King Abdullah Economic City, and King Abdul Aziz International Airport. Each one had to serve a purpose far beyond simply boarding passengers. These stations needed to handle the extraordinary surges of pilgrims arriving for Hajj and Umrah. Sometimes hundreds of thousands of people moved through the system within a matter of days. The station in Medina became one of the most architecturally striking elements of the entire project. Its design drew on local desert aesthetics, with a roof structure evoking the form of tents. It was built to provide shade and reduce heat gain in a region where direct sunlight can make surfaces unbearable to touch. Construction crews erected massive steel support frames. They then layered them with insulated cladding designed to reflect solar radiation.
This cladding reflects solar radiation while letting light in.
This cladding still allowed soft, diffused natural light into the concourse below. Every station required heavy-duty cooling and ventilation systems. Keeping vast indoor spaces comfortable in extreme desert heat is a significant engineering challenge. This demanded industrial-scale air handling units, insulated building envelopes, and carefully planned airflow. The airflow was designed to prevent hot air from pooling near platforms. Inside, the stations took shape layer by layer. Foundations were poured deep enough to support heavy passenger loads and the surrounding infrastructure. Platform edges were built to exacting tolerances to align safely with train doors moving at high-speed approach. Escalators, elevators, security screening areas, ticketing halls, prayer spaces, and waiting areas were installed. These facilities managed enormous crowds efficiently, particularly during peak pilgrimage seasons. Passenger volume multiplies dramatically during these times. Beyond the stations themselves, the technological backbone of the railway was taking form. The trains selected for the Haramain line were built for sustained high-speed operation. This required an electrified system capable of delivering consistent power across the entire corridor. Substations were constructed at intervals along the route. They stepped down and distributed electricity to the overhead catenary lines. A centralized signaling and train control system was integrated. It managed spacing, speed, and safety across multiple trains operating simultaneously at high velocity. Communication networks were built to give operators real-time visibility into every section of track. They also tracked every train position and every system status. Sensors embedded along the line monitored rail temperature, track alignment, and structural stress. These sensors fed constant data back to control centers. None of this technology was visible to a passenger glancing out the window. But without it, a desert railway moving at more than 180 miles per hour could never operate safely. The stations gave the project its public face, but this hidden network of power, signaling, and monitoring gave it its pulse. With the stations rising and the corridor electrified, the project entered its final and most demanding phase, proving that everything could work together safely under real desert conditions. Engineers beg and running test trains along completed sections of track, gradually increasing speed with each trial. At first, trains moved cautiously, checked at every stage for vibration, alignment, and structural response. Sensors monitored rail temperature as the sun heated the steel throughout the day, tracking how much the rails expanded and whether the system could compensate without distorting the line. Testing in the desert brought challenges unlike almost any other railway on Earth. Engineers had to verify that trains could maintain stability during sudden crosswinds and sandstorms.
Testing trains in sandstorms ensures they stay stable and safe.
Conditions that can reduce visibility to nearly nothing within minutes. Braking systems were tested repeatedly to ensure reliable stopping distances even when fine desert dust settled on the rails. Cooling systems inside the trains and stations were pushed to their limits during peak summer heat, confirming that passengers could ride in comfort even when outside temperatures soared past 120 degrees Fahrenheit. Every signal, every sensor, every safety system had to perform flawlessly before a single paying passenger could board. Eventually, full-speed trials began, with trains reaching their top operational speed across long desert stretches, cutting travel time between Mecca and Medina down to roughly 2.5 hours, a journey that once took most of a day by road. When the railway finally opened to passengers, it transformed how millions of pilgrims experience Hajj and Umrah, replacing long, exhausting bus rides through congested highways with a fast, air-conditioned, predictable journey across the kingdom. For elderly travelers and families, this shift mattered enormously, turning a physically demanding pilgrimage into something far more accessible. The Haramain Railway represents more than steel and concrete laid across sand. It stands as proof that even the harshest environments on the planet can be reshaped to serve human movement and connection. Every dune that was stabilized, every viaduct that was raised above a flash flood channel, every kilometer of rail welded to resist desert heat reflects a singular determination to make distance disappear in a place where distance has always meant hardship. This is not simply a railway, it is a bridge across time, linking ancient pilgrimage routes to 21st century engineering, and proving that even in the world's most unforgiving deserts, human ambition can lay down a path of speed, comfort, and connection. If you enjoyed this journey through one of the most remarkable railway projects ever built, follow the channel for more incredible engineering stories from around the world. Thank you for watching, and I'll see you in the next project.